As you can see over here, we have extracted the arrhythmia signal, congestive heart failure signal, and normal sinus rhythm signal. And I've also plotted over here the normal sinus rhythm. If you see, ECG signal basically consists of three regions. I could say the P region, a peak over here, followed by QRS complex wave, and followed by T. Let me explain you what it has. So P wave is represents as atrial depolarization. Complex QRS represents ventricular depolarization, usually the tallest peak. T wave represents ventricular repolarization. We don't have to worry at the moment because most of us may not be the expert from the medical field and who has a lot of understanding about this particular signals. But I still want to visualize them, and I've shown you you can plot them, or one another way is go to signals and try to understand if there exists some minor difference. How this could be understood? This could be understood using Signal Analyzer app. So let's go to Signal Analyzer app over here. Launch the Signal Analyzer app. And then what I want to do is I want to compare all these three signals. So the first one is arrhythmia. Next is congestive heart failure. And then I have this normal sinus rhythm. Let me start with the normal sinus rhythm. And I'll also try to plot it over here. And let's expand it. What do we observe? We have to observe, look at this peak. So one is R peak, this is R, Q, R, S, T, and again PQRSST repeats. You can observe that if I talk about this NSR, I could see that the distance is same across all the R peaks. Waveform is very consistent. Let's go ahead and try to plot. I'll go to section break. And what I'll do is I will try to plot over here congestive heart failure or arrhythmia. I want to plot this. So plot arrhythmia signal. Let's try to expand it. Now, if we try to compare it with normal sinus rhythm signal, look over here in NSR, the distance among R peaks was same. If we come to arrhythmia, we see that the distance between R peak is not same. You can see over here, this is small, over here it widens a lot. So this actually indicates that this is an abnormality in the signal. Also, if I look at this PQRS, we could see that the level is a bit shifted over here. Also, I could see some ripples. What about congestive heart failure? So if I plot congestive heart failure, okay, this signal is very bad. So the P wave is missing, almost unable to differentiate the QRS signal. You could observe over here that even this signal is, this region is not good. And since I am not a expert over here, uh, getting further details become difficult for me. But imagine that you are the one who have been assigned a task to build up a machine learning classifier or use, you can say, a convolutional neural network or a LSTM network to classify ARR, CHF, and NSR signals. Now, we have come to a point where we are talking about feature extraction. So in order to train a machine learning classifier or a neural network, we have to extract features from the raw data. And when they are signals, and if we are not the domain experts, so I am trying to keep everything in layman language so everybody should understood this. Okay, so the theory, a lot of theory is not going to help us over here. If I compare all these three signals, I am able to understand, okay, they are not same, but fine, because we have explored them. So one way that we could extract the features is go to this TF tab, and over here you will find out spectrograms and scalograms. Go to scalogram section and plot scalogram for arrhythmia, plot scalogram for CHF, and plot scalogram for the normal sinus rhythm. And now when you look at the scalogram, you very well understand, okay, they doesn't look same. And this is a easier way of interpretation. So most of the time you'll find out that when we have to use CNN to classify signals, and if signals are very complex, the best way would be to represent them into time frequency. So here we are not losing any information. We are just trying to convert 1D signal to a 2D signal kind of thing. Or here you see you have two colors over here. One is if you look at this burst over here, okay. So this one particular region represents one ECG cycle over here. So NSR, we see no abnormality over here. If we look at ARR, the first one on the left hand side, okay, this is bit comparable to NSR, but I see that there is some spreading out of this color over here, which is indicating some disturbance in the signal. And we look at that congestive heart failure signal, this is really, really bad. Now, this is what we wanted to explore. And now what we could do is, there are a lot of samples like this. So what I need to do is I need to understand, like, if I want to convert all the signals into their respective time frequency image and fed that as an input to CNN, then I need to write some code, because up till now we have hardly written any code. So what we could do is we could go to this generate script, and if you click on this scalogram script, it will generate a script for you, and this is the script. And it explains that this script has been generated by signal processing toolbox, where you are computing a scalogram. You can look over here, okay, because this was the range that we have selected, that we want the samples from 1 to 1000, right? And then we are taking all rows and columns over here. Wonderful. This is region of interest. So time 1, actually this is indicating 1, and over here it is indicating 1000. So this is what we are extending region of interest. Next is we convert cycles, we convert to cycles per seconds, right? And then what we do is we use this particular function, which is that function CWT. So this is constant wavelet transform. So here we are using what? CWT over here. So that's all for this particular part. In the next part, we'll be talking about how we can use a small script to automatically convert all the samples to their time frequency. I'll show you them. And after that, we'll move to the neural network part. Thanks.